Okay, we are live.
Okay. Hi, everybody. I'm Kate Kirby. I'm a principal statistician with the Center for Statistical Consulting here at UCI. And we're lucky enough to have Chuck Huber give another one of his wonderful presentations on survey statistics today. And I'm going to give a brief introduction about Chuck. He is the Director of Statistical Outreach at Stata Corp and an adjunct associate professor of biostats at the Texas A&M School of Public Health and at the New York University School of Global Public Health. In addition to working with Stata's team of software developers, he produces instructional videos for the Stata YouTube channel, writes blog entries, develops online net courses, and gives talks about Stata at conferences and universities. Most of his current work is focused on statistical methods used by behavioral and health scientists. He's published in the areas of neurology, human and animal genetics, alcohol and drug abuse prevention, nutrition, and birth defects. Dr. Huber currently teaches survey sampling at NYU and introductory biostats at Texas A&M, where he previously taught categorical data analysis, survey data analysis, and statistical genetics. Thanks so much, Chuck, for being here today. I'm going to pass it over to you.
Thanks, Kate. Thanks for having me again today. So today we're going to talk about one of my favorite topics, survey sampling. We just did a whole series on causal inference stuff, and we're going to shift over to survey sampling now. I'm going to turn off my video and share my slides. Whoops, sharing's not turned on. I think I need to be co-host or something in order to share my slides.
Yep, give me 1 sec.
Okay, no problem.
You should be all set now.
Okay. Yes, there we go. Okay, thanks. Okay, can you see the slides okay?
Yes, we can see them.
Slides are okay, great. Okay, so today we're going to talk about one of my favorite topics, which is survey sampling. I've actually taught this as a full semester course at both Texas A&M and at NYU, and I really enjoy this. It's not usually statisticians' favorite topic to talk about, but it is mine. Usually statisticians like survival analysis and multi-level modeling. So I pasted this link into the chat window, so if you just go there, you can click this, but if not, you can do a quick screenshot. You can download all the slides, the data sets, and the do files and all the materials here at tinyurl.com/survey sampling intro. So I thought, because this is a fairly lengthy talk, there are a lot of slides. I thought, and it makes it seem more complicated than it is, maybe in a way. I thought I'd put everything in one slide. This is sort of everything you need to know, all condensed into one slide, because this is how easy it is to do survey statistics in Stata. So you use your data set, use is at the top, and then you issue the svyset command. I call it the survey set command. And that's where you tell Stata about the characteristics of your data set, the survey sampling characteristics. And I'm going to define all of these things shortly. So if you don't recognize these terms, there's no reason you should. But anyway, you use SVY set to tell Stata about the characteristics of your survey sample. And then from then on, you just type SVY colon in front of your usual Stata commands. And the usual Stata commands will then take all the survey information into account. So any kind of sampling weights or strata or finite population correction factors, all those things will then be used in the process of calculating whatever statistic you've requested. So if I wanted to calculate a mean, I would just type SVY colon and then use my usual mean command. If I wanted to do a table using tabulate, I just type SVY colon tabulate, just like I would with the regular tabulate command, and it incorporates all the survey information. Same thing with regress. If I want to fit regression models that take all that into account, I just type SVY colon in front of my regress command, and it just works. It just takes all that information into account. If I want to use margins after I've fit a regression model that has survey characteristics, then I need to make sure I use the VCE unconditional option with margins. But other than that, that's how simple it is to do survey, to incorporate survey weights, strata, and things like that into your analyses. So that's it. I hope you enjoyed the show, and we'll see you next time. Well, it's a little more complicated than this, but in a nutshell, that's kind of it. Now, there's a little bit more to this. Often in the modern world, we have to deal with missing data. And this is a gross oversimplification, but not by a lot. If you have to deal with missing data, you can actually do multiple imputation with survey weighted data. So there's a variant of svyset called svyset. And so that allows you then to use multiple imputation with the survey features. So then you would type mi impute to run your imputation model, and then to do your estimation, you just type mi estimate colon svy colon, and then whatever your regression command or logit or probit or whatever command you would have used, that's what you use after mi estimate colon svy colon. So you can even do things like multiple imputation and other things with survey weighted data. So this is a way of saying that survey is integrated throughout all of Stata. When developers write a new command, there's a checklist that they have to sign off on before they submit it to be incorporated into official Stata. And one of the questions is, have you made your command work with survey weights? And if the answer is no, if they have not, the only acceptable reason for it not to accept survey weights is if there's no statistical theory to support that. But if there's statistical theory to support it, all new Stata commands are supposed to be to incorporate or allow the use of survey weights. So it's incorporated throughout. Okay. By the way, I didn't mention this earlier, but if anyone has any questions along the way, please just unmute. Feel free to unmute your microphones and ask away. Happy to be interrupted and would rather answer questions while the slide is up. So, okay, so let's kind of start with a rather provocative statement here. So I'm going to state that a random sample is not necessarily equal to a representative sample. And a lot of times I will get people that enjoy arguing this point. And the example that I often use is a poker hand. So this is what's called a royal flush. If you're playing poker, this is a hand that's called a royal flush. And this is really good news if you get a hand like this because you win. And depending on how much you bet, you'd win a lot of money. But the point here is that it is a random sample. Especially if you're in Las Vegas or Monte Carlo, I guarantee you that this is a very random sample, but it's not a representative sample of the deck of cards, right? Because a representative sample would have some hearts, it would have some clubs and some spades and some diamonds, might have a 2 or a 5 or other cards in there. So this is a royal flush dealt from a well-shuffled deck is a random sample that is in no way representative of the deck of cards that it was sampled from. And that's what survey sampling is all about. We want to go beyond just random sampling. We want to go to some effort to make sure that we get a representative sample and do that very carefully. So that's really what survey sampling is all about. So why do we care about this? Well, if our sample is not representative of the population that we draw the sample from, then we can draw incorrect inferences about the population. Remember, in inferential statistics, as the word implies, inferential, we'd like to draw inferences about the population from the sample that we draw. We don't really care about the sample so much. What we care about is the characteristics of the population. The sample is just a means to an end. So what happens if we have a population that we happen to know is exactly 50-50 males and females? 50% males, 50% females. And let's say that we also happen to know that the average height of males in the population is 160 centimeters, and the average height of females is 151 centimeters. Well, if we were to calculate the average height in the population as a whole, we would multiply 0.5 times 160 plus 0.5 times 151, which would give us an average height in the population of 155. Okay, it's a weighted average, half males, half females. So the population average height is 155. But what happens if we draw a sample from that population and our sample happens to be 25% males and 75% females? Well, let's say that sample happened to have exactly the right average male height and the exactly correct height for females, 160 and 151. The only difference is that the proportions of males and females are off. Well, when we calculate the overall average, it's going to be 0.25 times 160 plus 0.75 times 151, the overall average is 153. So the average height in the sample does not match the average height in the population. And it's not because the heights are wrong, it's because the proportions of males and females are wrong. The sample is not representative of the population, at least in terms of the proportion of males and females. And so that's one of the things we want to be really careful of is drawing a sample that accurately reflects the characteristics of the population so that we can draw correct inferences from our sample about that population. Okay. So in order to do this, we're going to use something called a probability sample. And you probably have never given this much thought before, but what we typically do in the world of statistics is called a non-probability sample, meaning that if we imagine our target population, so the population that we're interested in, usually we can't characterize the population precisely. There are always going to be some people that we can't find for whatever reason. People, members of the homeless population. They're just people without cell phones or phones or whatever. And so we typically refer to a sampling frame as a close approximation of the target population we're interested in. And then we're going to draw a sample from that sampling frame. Well, if we knew the number of people in the sampling frame, we could calculate the probability that any particular person in the sampling frame makes it into the sample. But if we don't know the size of the sampling frame, we only know the size of the sample, that's called a non-probability sample. And that's what we typically do in statistics. Most of our statistical methods that we learn assume a non-probability sample. Okay. Now, in survey sampling, we are going to deal almost exclusively with probability samples. And what we're the process, the way the process usually works is we first define what is the thing we're interested in and what is the population we'd like to study that in. So survey sampling folks are very interested in a well-defined target population. And then from that target population, we define a sampling frame, which is as many people as we think we can actually identify in the target population. And we usually know, not usually, we almost always know the size of the sampling frame, and we're going to call that big N. Okay. And then we're going to draw a sample of size little n from that target population or that sampling frame, capital N. So if I know both of those numbers, I can define or calculate the probability that any particular member of the sampling frame is actually sampled. It's just little n divided by big N. Okay. So that's probability sampling, and it's an important characteristic of survey sampling. Okay. So, and that kind of differentiates it from the rest of the world of statistics. So here's what we're going to do. And I know this looks very long, but the second half goes very quickly once you understand the first half. So I want to start off by talking about the NHANES study and the data set that we're going to be using, because it's a really classic example and maybe even the gold standard of the survey sampling world. And then we're going to walk through the survey sampling concepts, things like sampling designs. What's a stratified sample? What's a finite population correction factor? What's a sample weight and how do we calculate those? What are the different ways we estimate variances? Once we nail all that down, analyzing the data in Stata at least turns out to be trivially easy, and we'll go through that at the end. Okay, so let's first talk about the National Health and Nutritional Examination Survey. It's often called NHANES for short. This is collected by the United States Centers for Disease Control, CDC. It's been going on for decades now. There are many, many waves of this. And the nice thing is the data are all freely available on the web, and I'll show you more about that shortly. The way this study is actually conducted are they have these, they call them mobile examination centers, or MECs for short. They're actually these tractor trailers that they haul around behind big trucks, and they park them side by side. And if you look at them from above, this is sort of a diagram of how they're put together. They connect these four trailers with walkways, and the trailers each contain different things. There's a section for doing body measurements, reception, there's dietary interviews, interview rooms, there's a dentist, bone density, liver ultrasound, hearing. There's a lab in these things. There's a place where they draw blood. So it's a mobile examination clinic or center where they actually go in and not just measure you like how tall you are and how much you weigh, but they do blood draws and an extensive uh, I'm blanking on the word, but they measure a lot of things, not just how tall you are and how much you weigh. Once that data is processed and cleaned, it's actually available freely on the internet. You don't have to fill out any kind of forms. You don't have to get a password or register or anything. It's just sitting out on the web, and you can go get it right now. So this is the website for the 2015-2016 wave of data. And this is what the website looks like. And there's a link. You can click the link at the bottom, and it'll take you right to this web page. Now, if you go to the web page, notice on the left-hand side, there's kind of a menu here. We're in the 2015-2016 wave, and then there are a bunch of things available for that wave. There's demographics data, there's dietary data, examination data, laboratory data, questionnaire data. There are some limited access data where you do have to register, but that's the vast majority of the data is freely available without any kind of registration. So once you click on one of these links on the left, it then shows you all the various tables, data sets that are available. So just for the questionnaire data, that's what we're looking at here. There's a data set for things like acculturation. There's a data set for alcohol use, audiometry, blood pressure and cholesterol, cardiovascular health, consumer behavior. It's not just health stuff. There's consumer behavior, current health status, dermatology, diabetes, diet. There's a drug use questionnaire in here. Loads and loads of data just sitting there on the internet. And there's a link here at the bottom to take you to this page. And you can import that data very easily into Stata. And I'm going to show you how in a moment. Now, once you import the data, you are going to have to do a bit of data cleaning because it's not labeled when you download it. So you're going to need to go through and check out the key here for the data documentation so you can label things correctly. So for instance, the variable RIAGENDR is gender, and 1 represents male and 2 represents female. So you're going to need to go through and read these and label them clearly, but it's not, it takes a little time, but it's not that big of a deal. So how do I actually go through and do that? Well, if I wanted to download this particular wave of data, the body measures data, I would just go into Stata and type import, and these are stored in SAS transport files. And I happen to know from experience that these are SAS transport version 5 files, not version 8, they're version 5. So SAS export 5, and then just give it the URL. Just tell it the website. In fact, if you go back to here, you can right click on any of these data tables and you can select copy the link and paste that right into here. And Stata will import that data set right across the web, right into Stata. And then I can sort the data by SEQN as the ID number for each person. And I can save it as a Stata data set. And then below that, I have another import statement where I import the demographic data, sort it, save it as a Stata data set, and then I can merge those into a single file. And you could do this over and over and import tons and tons of this data. So if you can do everything on this slide, you can download mountains of data off of the NHANES website and then go through and analyze it. Okay. So this is some of the data that are in those files that I just downloaded. The SEQN is the respondent sequence number. It's like an ID number. And then there are variables for gender, age at screening, full sample interview weights, and things like that. And we'll come back and talk more about these interview weights and masked variant pseudo PSUs and strata here shortly. But that's all available in this data when you download it. Okay. So that's the NHANES data, and that's what we're going to be using. So let's now talk about some sampling concepts. And what I want to do is use Stata's svyset dialog box to sort of guide us through these concepts. So when we open this svyset dialog box, the first thing we see in the main tab at the top is the number of stages. Well, what does that mean? We'll talk about that in a moment. And then there's a box here for primary sampling units. Well, what is that? Strata, finite pop correction. What is that? Sampling weights. So we're going to go through and talk about the concepts so we can fill in this dialog box and set up our data so that we can analyze it with Stata. So the first thing we need to talk about is at the very top, it says number of sampling stages. So what is that? What's a sampling stage? Well, to do that, talk about that, we need to go through sort of what I would call the four major sampling designs. There are many, many variations of these, but these are sort of the basics. So there's simple random sampling, systematic sampling, cluster sampling, and multi-stage cluster sampling. So a simple random sample means that I'm going to select from a sampling frame a sample. And every person, observation, animal, refrigerator, whatever in the sampling frame, every element in the sampling frame has an equal probability of being sampled. And that's what we mean by a simple random sample. So let's say that we had a sampling frame of these 20 people. We have 20 names and we want to draw a sample of size 5 from this this sampling frame. One way I could do this is to just put the names on a piece of paper, throw them in a bowl, shuffle them around, and then draw 5 pieces of paper out. That would be an old-fashioned way to do it. A more modern way to do this would be to put the names in Stata, assign each name a random number, pseudo-random number to be precise, assign them each a random number, sort them by the random number, and then select the first 5 if I wanted a sample of size 5. So that would be a more modern way of drawing a simple random sample of size 5 from the sampling frame of 20 people. Okay. Now, there's an advantage to this. You don't have to know anything about the population, really. You just need a list of them, and that's about it. But there are some disadvantages to this. One, it may not capture certain groups of interest. If you have a very small subgroup within the population, your chances of finding them with a simple random sample may be small, and you may miss them altogether. It's also not very efficient. What we literally mean by a simple random sample, if we say every person or element in the sampling frame has an equal probability of being sampled, that means if I wanted to draw a simple random sample in the United States, that means I might have to hop an airplane and fly out to Bozeman, Montana, and drive 200 miles down some dirt road to ask a questionnaire of one person who lives out in the middle of nowhere. Whereas somebody else may be in downtown New York City near where I live, and I just go, take the subway over and give them my questionnaire. But that's literally what a simple random sample means. Everyone in the population or sampling frame has an equal probability of being sampled, and that's rarely true in practice. And if it was, it would be incredibly inefficient, both cost-wise and just the ability to go around and find these people would be difficult. Which also makes it very expensive in practice. Simple random samples are incredibly expensive, which is why we rarely see them. So there are other designs that help us get around some of these disadvantages. First up is systematic sampling. So let's say we had that same sampling frame. What we could do is pick a random starting point. Let's say we pick the number 3 as our starting point. And then we're just going to go systematically select every 4th person in the list until we get to a sample of size 5. Okay. So that's a way to do a systematic sample. And in this case, we would end up with these 5 people on the right. Now, there are some advantages to this. We also don't really need a complete sampling frame. This is often done with an emergency room. Let's say you wanted to sample people in the emergency room for a week. Well, you don't know who's going to come into the emergency room in advance. You may have an idea of how many people typically go through the emergency room in a week, but you don't know who those people are. So you don't have a well-defined sampling frame. But what you could do is say, okay, if I typically get 50 people through the ER in a week, I'm going to sample every 5th person so I get a sample of size 10 or something like that. So systematic sampling is often done in situations like that, where you have some idea of how many people will go through, but you don't have an actual list of them. It is easy to analyze the data and compute standard errors, especially with modern software, and it generally has fairly high precision. But the disadvantages, there may be some sort of periodic ordering to the elements in the sampling frame that create biases. A common example of this is when you have, if you wanted to go to the doctor's office and draw a sample of people from a doctor's office, and you're going to sample people on the 5th and the 22nd of every month. Well, it's a well-known phenomenon that people who are of lower socioeconomic status typically go to the doctor right after they get paid. So around the first or second of the month and around the 15th or 16th of the month. And so timing matters to people who are of lower socioeconomic status. So if I'm drawing my sample only on the 8th or ninth of the month and the 22nd of the month, I may miss people, systematically miss people of lower socioeconomic status. So there may be certain kinds of periodic ordering in your sampling frame that can cause this problem. And because of that, you may miss certain groups of interest, and it may not be very efficient in terms of just a practical nature for reasons like that. So that then brings us to cluster sampling. So what do we mean by cluster sampling? This is actually very popular, and it gets us around some of the logistical problems of simple random sampling. So rather than sampling individuals, what we're going to do is sample clusters first. For example, we might want to sample households. It might be easier in the old days, if you had a phone book, it might be easier to find a household and that rather than individuals, and then sample individuals from within the households we sampled. So it's a sort of two-stage design. At the first stage, we're going to sample households. So we make a list of all the households, and let's say we sample the Lennon household and the McCartney household at stage one. So now we have our sample of households. Then from within each of those clusters or households, we're going to sample an individual from within the clusters. So we would refer to this as a two-stage cluster sampling design, which is where the term stage comes in, and that's something we're going to need to fill in our dialog box, our svyset dialog box. Okay. Now, this has some advantages, the main one being that it lowers field costs and it increases feasibility. Simple random samples, as I mentioned before, can be incredibly costly and logistically just not feasible. So it enables sampling of groups of individuals for which you may not have detail for the individuals themselves. You may know the size of the population of Montana, but you don't have a list of every individual in Montana. But you know the total number of people, and you may know the households or something like that. Now, there are some disadvantages. It introduces more complexity in analyzing the data for sure and computing standard errors. And this is largely not a problem these days because of modern statistical software. In the old days, when you had to do this by hand or with a calculator or something, this could be very tedious. But with modern software, this is really not a big deal. It can have higher standard errors due to correlation within the cluster. So if you think about everyone that lives in your household, especially if you live with your family members, you're generally fairly correlated. And so with regard to things like your blood pressure, if you're all related, you're similar, have similar genetics, similar diet. So your blood pressure of everyone in that household is going to be very similar. Well, if it's very similar, if I were to sample more people from within that cluster, I'm not really getting much more information, right? Because if it's correlated within the cluster, sampling two people from within the same cluster doesn't really give me two full people's worth of information. It gives me two people's worth of correlated information. So a consequence of that is you end up with higher standard errors because you're not gathering as much independent information, which gives it low precision. Okay, so that's basic cluster sampling. Now we can combine this with this multi-stage approach. So we can do a multi-stage cluster sample. And in fact, that's how NHANES is collected. NHANES is actually collected in 4 stages. So from within the United States, at stage 1, they sample counties from around the United States. So the stage 1 is sample counties. Then from within those counties at stage 2, they're going to sample segments. These segments could be something like a school district or a statistical metropolitan sampling area, these SMSAs, could be a voting precinct or things like that. But the counties themselves are then subdivided, and at stage 2, they sample segments of those counties. Then from within those segments at stage 3, they sample households. And then at stage 4, they sample individual people from within the households. So the NHANES sample is a 4-stage sample. It's fairly complex. Okay. Now, how would we go about actually doing this? Well, let's say that on the left, we start with counties. So we select 15 counties. And then I zoom in on county number 7 from within county 7. Maybe it's a really big county and it has 25 census blocks. So from within county 7, I might sample, or it has 360 census blocks. I'm going to sample 25 of them. From within those 25 census blocks, I'm going to sample 10 households from each of those census blocks. And then from each of those 10 households, I'm going to sample a person. Okay. So that's how we would go about the nuts and bolts of selecting a multi-stage cluster sample. Now, how do we then tell Stata about this? Well, that means we would need to go back to our svyset dialog box and tell it we have 4 stages to our sample. And notice once we've changed the number of stages to 4, it then expands the number of boxes. So there are boxes for each of the 4 stages. Now, in my data set, I actually have variables for county, census, household, and person. So these are the IDs. So I have county ID, I have a census ID, I have a household ID, and a person ID. All of those variables are in my data set. So if I were to tabulate, for instance, county, there are 15 of these counties and 600 some odd observations within each county. So to fill that in, within the dialog box, I would select at stage 1 is the county, stage 2 is census, stage 3 is household, and stage 4 is person. Okay. And the order is important here. Stage 1 would not be person. You wouldn't start with person. You start with sort of zoomed out, and then you zoom in as the numbers get higher. Okay. So that is filling in the number of stages and the primary. Oh, I forgot to define this. Primary sampling unit refers to the ID. So at stage 1, the primary sampling unit is the county. And I have an ID for each county in the data set. That's the primary sampling unit. At stage 2, the primary sampling unit is the census block. Okay. So any questions up to here about sampling designs? Okay, I'll take that as a no. So next up, let's talk about stratification. So that's the next box or the next set of boxes in my svyset dialog box. Remember I said earlier that a random sample does not necessarily equal a representative sample. It can, but that's only if you're lucky. So let's say that we have this study population, and we happen to know from census data or somewhere that the number of males and females is exactly equal, and the proportion of males and females is equal for ages 15, 16, and 17. So we know that's the characteristic of the population. If we were to just go out and draw a simple random sample, we could end up with an age and gender distribution that's completely screwed up. And I've used the boxes, the shape or the size of each of the boxes to sort of represent the number of people or proportion of people. So we could end up with way too many 17-year-old females and way too many 15-year-old males and not enough 16-year-old females and so forth. So what we would like to do with stratified sampling is we would like to even this out so we can guarantee that we have the correct proportion of 17-year-old males and 17-year-old females, 16-year-old males, and so forth. So the way we would go about doing that is we would actually say, okay, I know I want a total sample size of, let's say, 60 people. So if I want 60 total people, what I could do is say, all right, I'm going to start sampling. First person I sample is a 17-year-old male. So the one 17-year-old male in that box. The next person is a 16-year-old female. So one person in that box. But once I fill in 10 within each of the boxes, once I've sampled 10 17-year-old males, that's it. No more 17-year-old males. Same thing with 16-year-old females. Once I get 10 16-year-old females, that's it. No more 16-year-old females. I'm just going to keep looking until I find 15-year-old females or 15-year-old males. So by stratifying and saying I'm going to only select a sample proportional to the study population, then I can trust my results a little bit better. At least I know that my sample is representative of the population with regard to the gender and age distribution. Now, it may not be the same with other characteristics such as race or things like that, but at least I know that with regard to sex and age, the sample will accurately reflect the study population. Okay, so that's what we mean by stratification. Now, if we were doing this with the NHANES study, we might stratify our counties as small and large. We might stratify our census blocks as rural or urban. Same thing with households. We might talk about single-person households or multi-person households, or single-family households versus multi-family households, like apartments versus single-family houses. And then people we could stratify by male and female. So we would simply stratify at each of these stages and then draw from within those strata at each of the stages. So this would be called a stratified multi-stage cluster sample. So again, it becomes much more complex, but the benefit is that we can be relatively reassured that our sample accurately reflects our population in some regard. So in our data set, we have the following variables. We have county underscore STR, so that's the county strata. We have the census strata, household strata, and person strata. And if I list the labels, I can see that county strata has small and large, census strata has urban and rural, household strata has single and multifamily structures, and person is stratified by male and female. So I have to have those variables in my data set, and when I do, I can simply select them in the boxes underneath strata in my svyset dialog box. Okay. So any questions about stratification? Okay, we have a quiet group this week. So let's talk a little bit about the characteristics of estimators for a moment. So the bias of an estimator is defined to be the difference between the expected value of the estimate and the value of the parameter that you're estimating. So let's say that we're estimating the population mean or mu. Remember that we use Greek letters to specify the characteristics of a population. So mu might be the mean in the population. That's the thing we're interested in. And we're going to estimate that with the sample mean x bar from a sample. Well, in statistical theory, we can actually calculate what is the expected value of the sample mean. Well, sometimes some estimators are actually biased slightly. So the difference between the expected value of the sample statistic and the population parameter is known as the bias. So it's important to note that any particular estimator may be unbiased for one sampling plan and biased for another. So that means that we need to pay attention to what sort of sampling design are we using, and then is a particular estimator, such as the sample mean, biased for a particular study design. Now, the other characteristic is bias versus variance. So let's say that on the left, we're going out and shooting arrows, we're archers, and we're shooting arrows, and on the left, we have a very tight cluster with the arrows all hit in a very small area, but it's systematically away from the center. So we would refer to that as being a high bias but low variance estimator. Sometimes that's desirable because sometimes we can actually calculate the bias and simply remove that bias. Now on the right, we would have an estimator or a person shooting a bow and arrow where we have relatively low bias. On average, the midpoint of those circles is the center of the target, but it's very high variance. They're all off by quite a bit. So that would be a low bias, high variance estimator. Now, which of these is better? Which do these prefer? Well, we generally quantify this using something called the mean squared error. The mean squared error is the sum. It's defined to be the sum of the variance plus the square of the bias. And that's how we usually evaluate different estimators for different study designs. So when you're designing these things, we would consider the mean squared error for a particular estimator for a particular study design. And this becomes very important when doing survey sampling, again, because different estimators have different characteristics for different study designs. Okay. Which brings us to something called the finite population correction factor. So that's the next column of boxes in our svyset dialog box. So what is this thing? Well, to talk about FPCs or finite population correction factors, we need to go back and talk about probability versus non-probability sampling. So remember, what we usually do is a non-probability sample where we don't know the size of the sampling frame. But in survey statistics, we typically or almost always know the size of the sampling frame. We're drawing a probability sampling, meaning that we know the size of the sampling frame, so we know the probability that any particular element is sampled. The other thing that we're doing with survey samples, whether we think about it explicitly or not, is we're sampling without replacement. So in order to talk about without replacement, what is sampling with replacement? So sampling with replacement mean, and this is how a lot of us think about statistics, again, not very explicitly. Sampling with replacement means that if I have a bucket full of 10 balls, 2 of the balls are red, 8 of the balls are green. If I draw a red ball and then I put the red ball back in, that's sampling with replacement. So after I've drawn the red ball and put it back in, the probability of drawing a red ball and the probability of drawing a green ball stays the same. 2 out of 10 for red and 8 out of 10 for green. So that's sampling with replacement. Sampling without replacement means that I'm not going to return the ball to the bucket once it's been sampled. So what happens then? Well, let's say that I draw a red, in the beginning, the probability of drawing a red ball is 2 out of 10, 2 red balls out of 10 total. But if I sample a red ball, now I have 1 red ball left among 9 total balls. So the probability of drawing a red ball changes. Well, let's say then I draw a green ball. I reach in and draw a green ball. Well, now the probability of drawing a red ball has changed again because the denominator changed. There's still 1 red ball in the bucket, but there are only 8 total balls in the bucket. So the probability of drawing a red ball changed. And this is what we do in practice. If we were to go out and sample a person, let's say we found a person walking around and we give them our questionnaire, we're not going to find that person again and give them our questionnaire a second time. We just wouldn't do that. So for practical purposes, when we do real life studies, we're sampling without replacement from a finite population. And these two characteristics lead us to need to adjust our statistical estimates for something called the finite population correction factor, or FPC for short. It corrects for the fact that we've drawn a sample without replacement from a finite population. Okay. So that FPC is defined to be big N minus little n divided by big N minus 1. So why do we care about this thing? Well, most statistics, sample statistics, actually can be defined more explicitly as the statistic, such as the variance. This is the variance of the sample mean using a simple random sample. It's technically defined as the statistic times the FPC times the bias. Well, it turns out the variance for the sample mean from a simple random sample is in fact biased. If you've ever wondered why is the variance formula for the sample n minus 1, remember the denominator is n minus 1. Well, why is it n minus 1 instead of n? Well, it's because it's slightly biased, and the bias is compensated by subtracting the 1 in the denominator. Well, there's also the FPC part of this. And so if we were to do all the arithmetic, what we're left with the variance formula, if we incorporate the FPC and the bias, is the standard population version, S squared divided by n, times big N minus little n divided by big N. Okay, that accounts for both the bias and the FPC. So again, the practical question is why? Who cares? Why are we doing all this extra math? Well, the reason that we care is let's look at an example where we have a study population of 100,000. And from that population of 100,000, we could draw a sample size of 50, 100, 250, all the way to 10,000. And in the second column, I've written down the infinite population standard error. And this is completely arbitrary. The numbers aren't important in and of themselves. What we're looking at here is the relative size of the numbers. So the third column is the finite population correction factor for a sample of size 50 from a population of 100,000, or a sample of size 100 from a population of 100,000. So that's the value of the FPC in the third column. The fourth column is the standard error adjusted for that FPC. So if we compare these, first off, let's look at the third column. The FPC for a sample of size 50 is 0.9995. That's essentially 1. So when we multiply that times our standard error, it makes essentially no difference. It makes a tiny change out in the 4th decimal place. So that's no big deal. But notice as the sample size gets larger for a fixed population size, the FPC gets smaller. So for a sample of size 10,000 from a population of 100,000, the FPC is 0.9. And that lowers our standard error from 0.0316 to 0.0300. Now you might be thinking, well, that's not a very big change. Well, the standard error has been reduced by about 10%. And sometimes that can make a difference. It can make your p-value a little smaller, just enough to maybe get you across the 0.05 threshold, and it shrinks your confidence intervals a little bit as well. So as a result, taking the FPC into account can actually be helpful to you on the data analysis end. It can reduce your p-values or shrink your confidence intervals. In the data or in the study planning phase, it can actually increase your statistical power by taking this number into account. And in almost all of Stata's power calculators, there is a box where you can put in the FPC, and it will account for the FPC when it does the power calculation. Now, there's this rule of thumb that says that unless your sample size is about 10% or more of your population size, there's really no advantage to taking the FPC into account. So in this case, once we get to 10,000, a sample of 10,000 out of a population of 100,000, that starts to kind of kick in, taking this FPC into account. Otherwise, it's probably not going to help you out that much. But just be aware that it is a thing. It just doesn't always it makes such a small difference for relatively small sample sizes that we just choose to ignore it. Okay. So this is that rule of thumb. So I actually have these calculated, and the variables are in the data set. So I have county FPC, census FPC, household FPC, and person FPC. It may be that at a certain sampling stage, the FPC might be helpful. Usually at the higher sampling stages, you're more likely to be drawing a larger number of the FPCs than at the lower numbers. Or maybe if you have 4 people in a household and you draw 1, the FPC might make a difference there. But the FPC can be calculated at each sampling stage, and we can fill those in our svyset dialog box. Okay, so any questions about finite population correction factors? Everyone's still awake? You guys are really quiet today. Okay, next up, let's talk about sampling weights. So sample weights, that's the box on the far right here. We're going to need to fill those in. Recall that we're talking about probability samples. So we know big N, we know little n. The sample weight is simply the reciprocal of the probability of being sampled. So if I sample 1 county out of 15 total counties, the sample weight is the reciprocal of that. It'd be 15 over 1, which is equal to 15. Okay. So you just flip the fraction over, that's the reciprocal. So in this case, it's really easy. One county out of 15 is the sampling probability, 15 over 1 is the sample weight. Now, what does that mean for practical purposes? What that means is that the 1 county that we sampled is representing 15 counties in the population. Okay, that's literally how you would interpret that sample weight. So the sample weight of 15 means that each county is representing 15 other counties. At the census block sampling stage, we could do something similar. So let's say that we sample 25 census blocks out of a total of 360. That gives us our probability of being sampled. The sample weight is simply 1 over that probability, or you just flip the fraction, 360 divided by 25. In this case, the sampling weight turns out to be 14.4. So what that's telling us is that each census block that we've sampled is representing 14.4 census blocks in the population at large. Okay. Similar idea with households. So let's say we sample 1,000 households out of a total of 11,500. To get the sample weight, we simply take the reciprocal. So it'd be 11,500 divided by 1,000. That gives us a sample weight of 11.5. So each household that we sample is representing 11.5 households in the population. Same idea with people. It's just the sample weight is the reciprocal of the probability of anyone being sampled. So that's the idea of a sample weight and how we would calculate it. I have that in my data set for each of these, so I just fill them in at the county level, the census block level, the household level, and the person level. Okay, so any question about sample weights? I promise we won't be doing this much arithmetic the whole time. In fact, that's kind of the end of the weird arithmetic. Okay, so variance estimation. If you click on the SE tab in the svyset dialog box, there are lots of different weird words or letters like linearized, bootstrap, BRR, jackknife, SDR. We don't have time to go through and define each of these because some of these are more like algorithms than formulas. So they stand for linearized first order Taylor series approximation or bootstrapping, jackknifing, balanced repeated replication or BRR, or successive difference replication or SDR. So, how do we know which one of these to use and which one is optimal for our study design? Well, the good news is you don't need to know really anything about this in order to analyze your data, your survey weighted data, because there really is no best method for a particular sampling design. It's a feature of the way the study was designed, and the people who design these studies are experts in this particular branch of statistics. I sometimes joke that survey statistics is a bit like the cardiovascular surgeons of the statistical world. This is a highly specialized area of statistics, and the design of these kinds of studies is very sophisticated. And the variance estimation technique is sort of built into the design. And so if you get a data set, your job is not to figure out which one would work best. It's the job of the person who designed it and collected the data to tell you which variance estimation method you should use with the design that they gave you for the data set. So what you need to do then is read the instructions. The instructions should, and almost always will, come with instructions. So for the NHANES study, for the 2011 to 2014 wave and the 2015 to 2016 wave, there is a manual, a PDF manual that comes with this. And one of the chapters is variance estimation. So if we go to that chapter and read it, it actually tells us, and I've highlighted it here, currently NCHS recommends using Taylor series linearization methods for variance estimation and analyses of NHANES, blah, 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 blah. So they tell you very explicitly, use the Taylor series linearization method for calculating the variance. So there's no mystery. We don't really need to understand it. We just need to select it in the dialog box and follow the instructions. Okay. Now, a lot of these large studies will actually tell you the svyset command. So the CDC actually, if you go to their website, it actually, Stata is very, very popular for you analyzing survey weighted data. And it's so popular that the CDC actually tells you what your svyset command should look like right on their website. So you really, in some sense, don't need to know any of these things. You just need to download the data, use the svyset command that they tell you, and then you can go about analyzing the data as long as you use that svy colon prefix. Okay. It's not always this simple. NHANES is very nice about providing this information, but it should be that easy. Most of the time for really large survey samples, it will be that easy. Just read the instructions, use the svyset command that they tell you, and you should be okay. Okay. So if we were to look at that entire command, that entire svyset command, this is what it would look like. And that looks big and messy, and wow, that's how would we ever, lots of opportunities for syntax errors, which is partly why I like using the dialog box. If you go back to the dialog box and just select everything here, it generates the command for you because that is a big command. Now, the other good news is that in reality, we don't have to type all that. And with the NHANES data, they've actually, for privacy reasons, collapsed those four sampling stages into a single stage. And the reason is that there are a lot of highly sensitive data in these data sets, things like drug screens and sexually transmitted infection questions and just general health questions. And people might not want to be identified. And so, to ensure the privacy of the respondents, they actually mathematically collapse the four sampling stages into a single stage. So the svyset command that we actually use in Stata for the real data is svyset PSU, primary sampling unit. Strata, I've conveniently named Strata. The weight is the weight, and I'll explain MEC here in a minute why I have different weights. And then VCE is linearized, and single unit means that's how we're going to treat missing data. We're just going to treat any single units as though they're missing within a particular strata. Okay. So I got a little ahead of myself there. So that's the basics of sampling concepts. So before we move into data analysis, does anyone have any questions up to here? For those of you looking at the time and thinking, oh gosh, this is going to take a long time, the second half of this goes by shockingly fast because once you've done the first half and set up your data, analyzing the data is actually very, very easy. So we'll be done in about 15 minutes if you're looking at the clock. Okay, so let's actually look at, I've actually downloaded a bunch of the data from NHANES and combined it into a single data set called Survey Intro. Um, and that data set is available in the download link that I sent you or showed you earlier. So here is a listing of some of the variables that are in the data set. I have the ID variable, that's the participant ID. PSU is what they call the masked variance pseudo PSU. That's a long-winded way of saying that's the primary sampling unit PSU, and it's masked so that we can't go back and figure out who these people were. Strata is the masked variance pseudostratum. So that's our strata variable that we're going to use. And then we have two different sampling weights. I've called them WT underscore MEC and WT underscore interview. The MEC weight, that is for the mobile examination center. So almost everyone in the data set got the interview. The interviews were done over the phone. So we have much more complete data on the interview. So that weight is going to be different than the MEC. The fewer people actually showed up at the clinics, the mobile examination centers. That's a smaller number of people, and so the sample weights are slightly different for the MEC. So any of the data collected at the MEC, things that have to do with the blood draws or hearing or things like that, we're going to need to use the MEC weights to correctly define or characterize the sampling features. If it's just interview data like the drug screen or things like that, or the things like your consumer preferences, things like that from the survey or the interview, we'd use the interview weights for those. Okay, so the weight depends on which variables that we're interested in. So to set this up at the top, I've shown how to do this with the dialog box, how to set this up. It would be one sampling stage. And then at the bottom, I've shown the actual command. So however you want to do it with the dialog box, or if you just want to type it in, that's this svyset command that we would use. Once we've typed that in, we're done. We're ready to analyze our data. So we can go about doing our means and tables and regressions and things like that, as long as we follow some basic rules. And we'll get back to those in a moment. I've tried to include a wide variety of variables here so that if you download this and you want to practice with this data set, there's kind of something for everyone in here. There are lots of things like the usual demographic stuff, sex, race, age, education, income, things like that, BMI, health status. But I also have things like more laboratory and measured things like systolic blood pressure, diastolic blood pressure, cholesterol, HDL, glucose, insulin, HbA1c, and so forth. There's dietary stuff in here, grams of protein consumed per day, carbs per day, sugars per day, fat, and so forth. There's a drug and alcohol screen in here, so those are included in the data set. All of these are in the same data set. These are not separate tables. They are all variables in that same big data set. There's a depression questionnaire in here, a 10 question depression screen. So that's in this data set as well. So if you want to download this from the zip file that I showed you earlier, all of this stuff's in there and you can play around with it. So let's start with basic summary statistics. So if I wanted to calculate the mean of age, rather than just typing mean age, I need to type SVY colon mean age. If I do that, what that's going to do then is it's going to incorporate all of that stuff from svyset into the calculation of the average age. Okay. So notice at the top, it tells me the number of strata, number of PSUs, but it also tells me the number of observations. So there are 9,971 observations in this data set, and those observations represent 316 million people in the population. I know the size of the population from the observations because if I take the sample weights for each of the observations and add up all the sample weights, that tells me the size of the population that this sample represents. Okay. So now if I look at the results below, this is the mean and mean age in the population. This is not the mean age in the sample. And if you want to prove that to yourself, drop the SVY colon and just type mean age and the number changes. because if you don't include SVY colon, you'll get the mean of the sample. But what we want is the mean in the population. So this reported mean, that is the mean age in the population, not in the sample. It also gives us a standard error and a confidence interval for that mean age, again, in the population. Okay. Now I could do this over race. So I could, as long as I use the SVY colon in front, I can use any of the usual options with the mean command. So I could do over race. C format just cleans up the display of the numbers, so I don't get a bunch of decimals in here and makes the table look messy. I could do this over race and female. So I could see the average age in the population for various combinations of race and gender. Now, what if I wanted to do this for a particular subpopulation like white females? Normally in Stata, the way you would do this, you could just type mean if race equals 2 and female equals 1. Any other time, that would be a perfectly reasonable thing to do in Stata. But if you're dealing with survey weighted data, changing or zooming in on a subpopulation changes the calculation of the weights because it has to adjust the denominator. And sometimes that's not done correctly if we just use if. So the SVY prefix has an option called subpop. So what we need to do is forget about the if command. When you're working with survey weights, just do not use if. Okay, use the subpop option if you want to restrict your analysis to a subpopulation. So the way I would suggest doing it is define your indicator variable first. So generate white female equals race equal 2 and female equal 1. So generate that indicator variable for white female and then use that in the subpop option of your SVY prefix. Okay. Now, I teach this as a course, and almost every time I teach the course, I get somebody who'll raise their hand and say, "Oh, I just tried it," and I get the same answer either way. And that happens sometimes. Sometimes you get lucky. The last time I taught this course was in Washington, D.C., and I used the example, you could blindfold yourself and walk across the street in downtown Washington, D.C., and you might make it to the other side of the street. It's possible you'll get to the other side of the street walking blindfolded. But it's not likely, and the consequences if you don't make it are pretty bad. Maybe not that bad with the statistical software, but the point is sometimes you get lucky using if, but don't count on it. Just eliminate using the if command if you're working with survey weighted data, and always use the subpop option. Okay, it's sometimes they're the same, but not always. Okay. Now I can use the SVY prefix with tabulate as well. So if I wanted to tabulate a variable like diabetes, I could do that. I use these format options to format and clean up the tables. I don't like having weird decimals, different numbers of decimals, digits to the right of the decimals. So I tend to put these format options in here, if you're just wondering why. But anyway, so what this shows me then is the proportion of people in each category. 91.6 or 0.916 people do not have diabetes. 0.084 or 8.4% of the population does have diabetes. Again, these are proportions in the population, not in the sample. You could switch these to counts if you wanted, rather than proportions. So there are all kinds of other options. Again, it tells you the number in the number of observations as well as the total number in the population. I can do other things. I could do cross tabulations of diabetes and health status. I could ask it to do certain statistics for me. I could do a Pearson chi-square or a likelihood ratio test with these. Now, you have to be careful with the statistical tests because we report the uncorrected Pearson chi-square. So at the bottom of the slide here, notice where it says Pearson uncorrected chi-square is 316. So that's if we just did regular old tabulate, that's the value the Pearson chi-squared we would get. We do not want to report that. What we want to report is the design-based F statistic and its p-value. Notice we don't give you the p-value for that chi-square. We only give you the p-value for the design-based F statistic. So what you really need to report is the design-based F statistic and its p-value if you wanted to look for association between diabetes and health status here. Same thing with the likelihood ratio chi-square. There's the uncorrected version and the design-based. So again, go with the design-based when you're doing table-based tests of association. Linear regression. So what if I want to fit a linear regression model for systolic blood pressure, including the main effect of age, the main effect of female, and the interaction of the two? Well, I would write my regression command exactly how I always do, but I would type SVY colon in front of that command, and then Stata will account for all the survey features. So the coefficients are listed in the table below, but notice it says linearized standard error. Those standard errors and the coefficients all take the survey weights into account. Everything will be wrong if you forget that. If you leave off the SVY colon, not just the standard errors, but even the coefficients could be wrong if you leave off the SVY colon. I taught this as a full semester course at NYU a couple of years ago. And on the midterm exam, I had a shocking number of students who just forgot to put the SVY colon in front of some of their commands. And I counted them as completely wrong. And some students were upset about this. Well, I just forgot. Well, if you forget, the numbers are completely wrong. So it's still wrong. You have to remember to put the SVY colon in front of the commands, and then everything just works. Okay. Now, if you use the SVY colon prefix in front of a regression command, and then you want to use the margins command after, and by the way, margins and margins plot are probably my two favorite commands in all of Stata because they allow you to visualize the results of your regression models very easily. So if you use survey weights with your regression command, and then you use margins, you need to remember to use VCE unconditional, that option in your margins command. Just put it in there. You don't really need to know too much about it or what it's doing. Just put it in there, and then all of your predictions, your marginal predictions, will be correct as well. I believe, I haven't done it in so long, I believe if you leave it off, it will actually remind you. I think it may throw an error. I don't remember now for sure, but I think it will remind you. Anyway, so then using margins and margins plot, you can visualize the results of your regression model. Same thing with logistic regression. Let's say you want to fit a logistic regression model for diabetes. Again, using age and sex as predictors, or age and female. Just put the SVY colon in front of your logistic command, and then use VCE unconditional with your margins command, and now you get a nice margins plot that accounts for all the survey features in your data. Okay. You can even do this with something as sophisticated as a generalized structural equation model. So here I've taken the depressions questions. So there are 10 depression questions, and let's say that I would like to create a latent variable called depression using those 10 depression questions, and then I want to use my latent variable depression as a predictor of health status. I can do that, and not only can I do that, I can actually treat the depression questions as ordinal. The questions are ordinal, and I can treat those observed variables as ordinal when creating that latent variable. And so if we look at the command here, the command is gsim, and this is what creates that depression scale. And notice all I have to do to incorporate the survey weights is put SVY colon in front of that giant gsim command, and it will incorporate the survey weights into all of this. Okay. And notice here at the bottom it says family ordinal link logit. So you can fit very, very sophisticated models, even using generalized structural equation models that incorporate survey weights. And you can even do predictions from these. So let's say we fit the model, and now we want to look at what is the relationship between our depression scale and health status. We could generate predictions from those. So here the vertical axis is the predicted probability of being in a particular health status category. Dark blue is excellent, light blue is very good, purple is good, orange is fair, red is poor. And then the horizontal axis here is the empirical Bayes means for our overall depression score, that depression latent variable. Again, all of this, if you're not familiar with structural equation models, don't worry about it. The point here is that I can use survey weights with even very, very sophisticated models. So I know that the numbers and standard errors and the confidence intervals will be correct. I'm not going to show an example here. In fact, I think, I took it out. But you can, if you need to do multiple imputation, you can do multiple imputation with survey weighted data. Again, this is a bit of an oversimplification, but these are the basic steps. You would need to use the mi svyset command rather than just svyset. Then you would use mi impute to fit the imputation model. to impute something like here we would be imputing the variable glucose, and then to actually estimate the regression model, including the imputed variable glucose, we would type mi estimate colon svy colon followed by our regression command. So you can even do multiple imputation if you have missing data. So if you'd like to learn more about this, Stata Press has a book called Survey Weights, a step-by-step guide to calculation. That's by Valiant and Deaver. They have a really good big yellow book. I think it's published by Springer on survey weighted data also. So a couple of those. This is, I often say, this is my favorite survey weight, and I have a bunch of survey books on survey data analysis. And if I could only own one, this would be it. It's by Herengo, West, and Berglund. I've never met any, I don't think I've ever met any of these three people. I don't get kickbacks for saying that. I have no financial ties to them, but in my opinion, this is probably the best survey data analysis book on the market. It's very clearly written. It's very comprehensive. It's huge. It's like 600 or 700 pages. And it's a remarkably good deal. I think on Amazon it's under $100. And it covers everything from the designs, the sampling designs at the beginning, all the way through doing things like imputation towards the end, and other specialty topics like survival analysis or analysis of longitudinal data with survey weights. So it's very comprehensive. I think it's very clearly written, and it's a pretty good deal on Amazon. This is a classic. When I was a student and took this back in the 90s, this was the textbook we used because back then, most of the focus was on the design of these kinds of studies. The software hadn't caught up with analyzing these kinds of sophisticated studies. The analysis was much more difficult, and the software just was not there to handle it. So we tended to focus on the design of these things. And this was the classic by Paul Levy and Stan Lemishow. Still around today, and if you're very interested in the nitty-gritty of the design end, this would be the book. On the other end, on the analysis, the Cornyn-Grabart is a standard book that's often used and cited. It's been around for probably 15 years as well, 10, 15 years. So that's another excellent reference if you're looking for references on this material. So again, you can download all the slides, the data sets, and do files at tinyurl.com/survey sampling intro. I'm not in any rush. I can hang around and answer questions as long as we like. And if you think of them later, shoot me an email at chuber@stata.com. So thanks for being here today, and I'm happy to take questions. Any questions? Margaret can attest to how slow I am at replying to emails.
It looks like we've got a lot of thank yous and some people signing off.
Okay. Let's see. Check materials. Slides today after the workshop. I'm just reading through the questions. I would just grab them from the link. I don't know if they're available right now, so just click on the link.
I'm
In fact,
actually going to send out the slides to everyone after once we conclude. I'll
Okay.
send the slides along with the recording to everyone.
Okay, here I'll paste the link in here again as well. So, all righty. Well, thank you very much, and I will see you next month. I don't remember what our I think structural equation modeling, is next month.
I think so.
I looked earlier when I was opening this. So, okay. Well, I guess I'll see you next month for structural equation modeling.
Okay, sounds great. Thank you, Chuck. Thanks,
Yeah,
everyone.
thanks for having me. Bye.
Bye.